Poisson's ratio. When a material it is subjected to uniaxial tensile force, it elongates in one direction. This is a material, it is subjected to uniaxial tensile force along the z direction. If this is the z direction, along the z axis, it is a longitudinal axis, there is an increase in length along the longitudinal axis. To maintain constancy of volume along the lateral direction x and y direction, the material is subjected to compression. If this material is isotropic and the force is unitensile force, then the strain along the lateral directions epsilon x is equal to epsilon y. So Poisson's ratio is given, it is represented by the symbol nu, and it is given as the ratio of lateral strain to the longitudinal strain. Lateral strain, it can be either epsilon x or epsilon y by longitudinal strain, that is epsilon z. Along the longitudinal direction, there is an increase in length, and in the other two directions there is decrease, there is a contraction. So epsilon x is equal to epsilon y if the material is isotropic and provided the force is uniaxial tensile force. So epsilon z is positive and epsilon x, epsilon y is negative. Poisson's ratio is ratio of lateral strain to the longitudinal strain. This minus sign is included such that Poisson's ratio is always positive, because lateral strain is negative and longitudinal strain is positive. So inclusion of this negative sign indicates that Poisson's ratio is always positive. So for the case of metals, this Poisson's ratio falls between the values of 0.25 to 0.35. For most of the metals, Poisson's ratio, it is in between 0.25 to 0.35. But this Poisson's ratio cannot be determined by normal or by routine tension test. The reason for this is it is very difficult to measure the elastic strains, because the elastic strains, they are very, very low. It is very difficult to measure these strains in a normal routine tension test. It requires very careful measurements, as well as the equipment to measure these very small strains should also be very sensitive. So very sensitive extensometers are used to measure these strains, as well as to measure these lateral strains. Strain gauges are to be placed. So this Poisson's ratio cannot be normally measured by means of normal routine tests, because it requires very careful measurements of these strains. Apart from this, the other observations is Young's modulus is represented by the symbol capital E, that is the modulus of elasticity, which is different for different materials, and G is the shear modulus. This is also different for different materials. Modulus of elasticity, shear modulus, and Poisson's ratio nu. This is also different for different materials. Even though all these three are different, all these three can be related to each other. So the relationship between the modulus of elasticity, shear modulus, and Poisson's ratio is given by modulus of elasticity E is equal to 2 times the shear modulus into 1 plus Poisson's ratio. So this is one relation which relates modulus of elasticity, shear modulus and Poisson's ratio. With this, I wind up the tension test and move on to the compression test. Now, what is the importance of this compression test and where this compression test is used? Compression test, it is used mainly in metalworking processes to determine the flow stress of the material, because in metalworking processes the material is subjected to very large amounts of plastic deformation. So in order to determine the flow stress of that material, instead of tension test, we normally go for compression test, because necking is one of the problem that is there in the case of tension test that limits the true strains to a very low value, to a value of about 0.5. So in order to have more uniform strain, compression test is used, because in most of the plastic working processes or plastic deformation processes, true strains are in excess of about 2. So with the help of the compression test, one can achieve true strains to almost to a value of 2, and thereby the flow stress in metalworking processes that can be determined by means of compression test. The strain rate when compared to the tension test, it is higher for the case of compression test. The various strain rates for different tests that has been discussed in the previous module, for the case of tension, for the case of creep, impact and compression. So when compared to tension test, compression test can be carried out at high strain rates, and the true strains that can be achieved, it is higher, because the material is subjected to excessive plastic deformation before failure. Whereas in the case of tension, necking, it limits the true uniform strains to less than 0.5. So compression test, it is carried out on a cylindrical specimen between two anvils. As you have already seen in the previous module, the video for the compression test, that is for the case of a copper specimen where it is compressed in between the two anvils. So this is the cylinder, initial height h0, height of the cylinder, and the diameter is d0. So when a compressive stress or compressive force is applied on the material, it undergoes a decrease in height and increase in cross-sectional area. The height reduces upon the application of compressive force and the diameter increases. So this is the final diameter d and this is the final height h. So the cross-sectional area increases in the case of compression and the height decreases in the case of compression when compared to tension, where in the case of tension test there is a reduction in cross-sectional area under the application of this tensile force and increase in length occurs in the case of tension. So in the case of compression test, when it is conducted for a cylindrical specimen between the two anvils, the diameter increases and the height decreases. But the problem which we have in the case of compression test is barreling occurs. Barreling means bulging. The specimen where it is in contact with that anvil, because of the presence of friction, it cannot flow freely. It cannot undergo plastic deformation freely. Whereas the specimen at the mid height, it flow freely, thereby barreling, that is a bulging appears. This is not the final shape of the specimen. It is not like this, but the specimen, it is barreled, it is bulged. So if a cylinder of height h0 and diameter d0, if it is compressed by means of a compressive force, then the diameter, it would be capital D, that is the final diameter, and height is h. barreling occurs mainly due to friction. This component, it is subjected to compressive force between the two anvils. This is the anvil and this is the anvil. The specimen is placed at the bottom anvil. This is the bottom platen, which is also known as anvil. Bottom platen or the anvil, where the specimen rests on it, and this is the upper platen or also known as upper anvil, by which means a compressive force acts on the material. Upper anvil or upper platen. So when this component is subjected to compressive stress, the material which is in contact with the anvil surface, the surface of the material which is in contact with the anvil, top and upper surface and the lower surface which is in contact with the anvil, cannot flow freely because of friction, which resists the outward flow of the material. The friction which prevails at the interface between the anvil and the cylinder surface, it restricts the free flow of that material. Friction acts in this direction, thereby does not allow the material to flow freely. Whereas the material which is at mid height, there is no resistance for it, so it can flow freely. Thereby this bulging or the barreling occurs in the case of tension. This is known as barreling. The main reason for barreling is due to the friction at the interface between the anvil and that of the surface of the cylindrical specimen. So when you consider two specimens which have the same diameter but different heights, consider two specimens having same diameter but different heights. Diameter is similar for these two specimens but of different height. In deforming both these specimens which have same diameter but different heights to same percentage reduction, the one which is shorter requires more load to cause the same amount of reduction than compared to that of the longer specimen. The reason for this is when these specimens, they are compressed by means of the compressive force, this portion, the surface of the cylinder which is in contact with the anvil surface, because of the friction, it cannot flow freely. So here we are having the undeformed region at the interface between that of the anvil and that of the cylinder surface. Because of the friction, the material cannot flow freely. There is some resistance to the free flow of that material. So here there is a undeformed region. Undeformed region. Undeformed region. So as the compressive force is applied on the specimen and reduction in height occurs, these hatched regions, which indicates the undeformed regions, because of the friction, they approach each other. For the case of shorter specimen, more is the undeformed region. These two hatched regions, they overlap. Thereby more is the undeformed region, so more load is required or more force is required to deform the material. Whereas in the case of longer specimen, lesser is the undeformed region because of specimen height is more. Thereby, as the reduction or the compression takes place, as the reduction is taking place, these two regions do not overlap in the case of longer specimen, whereas in the case of shorter specimen, these two undeformed regions, they overlap and they increase the stress required for further deformation or further reduction in height. So this increases the axial load required for further deformation in the case of shorter specimen when compared to that of the longer specimen. So this is mainly due to the presence of undeformed regions. For the case of shorter specimens, these undeformed regions, they come closer and they overlap, thereby axial load to cause further reduction in height, it increases. So to avoid this difficulty, D0 by H0 values should be as low as possible in order to minimize this problem. But as D0 by H0 ratio, this ratio, it becomes smaller and smaller, there is another problem. Because with respect to the diameter, if height keeps on increasing, if the height of the specimen keeps on increasing, then the problem is buckling occurs. So when a compressive force is applied on the specimen undergoes bending, buckling. So this is what happens for a longer specimen. As this ratio is lower, means if the height is more, if the height of the specimen is increasing, then instead of reduction, plastic deformation, the specimen tends to buckle. Buckling occurs. So this ratio, it should not be lower than 0.5. D0 by H0 should be lower. It can be lower mainly to avoid this problem, this undeformed region which requires more load to cause the same amount of reduction. But as this ratio is lowered, still the problem is buckling occurs. So in order to avoid this buckling, this ratio, D0 by H0 ratio, it should not be less than 0.5, or else buckling will take place. So according to the constancy of volume, D0 square H0 is equal to D square H. According to the constancy of volume relationship, for the case of a cylindrical specimen, D0 square H0 is equal to D square H. So compressive stresses, compressive tests, they are carried out for various specimens which have D0 by H0 values different. So a plot of axial load versus, this is the axial load applied to cause reduction in height, axial load along the y-axis and reduction in height along the x-axis, curves can be drawn for various values of D0 by H0. If one considers for the same material but different values of D0 by H0, then this is the different types of curves that are obtained for the same material for various values of D0 by H0. So the curves keeps on raising as D0 by H0 increases. The reason for this is already explained. As D0 by H0 increases, that means for the same diameter, similar diameter specimens, as this H0 value is lower, a shorter specimen requires more load to cause the same amount of reduction. The reason is more is the undeformed region. As these undeformed regions, they overlap, they come closer together, thereby more load is required to cause the reduction in height. So as D0 by H0, this ratio increases, this curve rises. So from this, one can determine the true compressive stress as well as the true compressive strain. P subscript C indicates the compressive stress, true compressive stress, and epsilon C indicates the true compressive strain. So compressive stress is equal to load, compressive load, divided by the cross-sectional area, pi by 4 d square. P is the load, compressive load, d is the diameter. So according to the constancy of volume relationship, this can be written as, so instead of d, we can substitute d square, it can be substituted for d0 square h0 by h. D0 square h0 square by h, where D0 and H0 are the original diameter and height, where h is height at any instant, that is the instantaneous height of the specimen. So this is the true compressive strain that can be determined from a plot of axial load versus reduction in height, and true compressive strain, this is the true compressive stress, and true compressive strain is equal to ln of h by h naught, h naught by h. So this is for true compressive strain, ln of h naught, initial height by height at any instant, that is h. In order to minimize this barreling, one can minimize this barreling by the application of lubricants between that of the anvil surface and that of the surface of the specimen. So these lubricants, they minimize the friction and thereby minimize this barreling. For the case of deformation, cold deformation, deformation at low temperature, room temperatures, Teflon sheet, it is used at room temperature. Teflon sheet, this is for low, that is for room temperature compression, Teflon sheet it is used. And moreover, the other factors that can be considered during this compressive test is to minimize this barreling. One is use of the lubricants, Teflon sheet, which is for low temperatures, that is for room temperatures, and for very high temperatures, glass is used. This is for high temperatures. But during the deformation, once this lubricants tears away, that is the Teflon sheet, it tears away from the interface, then it has to be replaced at regular intervals. As well as the platens that are used to deform the specimen, if these are the upper platen and lower platen for the case of compressive test, where on the bottom platen the specimen is placed and this is the upper platen which exerts a compressive force on the material. So if these platens, they should be smooth and not rough, because if they are rough, it increases the friction. Once the friction increases, then barreling, bulging occurs, and the specimen at the surfaces do not undergo deformation, and only the specimen at the mid height undergoes deformation and the barreling occurs. Thereby the platens, they should be smooth, as well as they can be slightly curved at the ends to retain the lubricant, such that the lubricant, it is not torn away during the deformation. So these are some of the precautions that are to be taken during the compression test to minimize this barreling: applying the lubricants, having the smooth surfaced platens with slightly curved at the ends so as to retain the lubricants. The engineering strain rate in compression is, strain rate is equal to velocity by L naught. So V is the velocity of the die which applies the compressive force on the component, velocity of die, and L naught is the L naught or H naught, which is the initial height of the specimen. So to carry out the compression test at constant strain rates, so there is not much problem for the case of engineering strain rates. But for the case of true strain rates, true strain rate, this is equal to velocity of the die by L, where L is, here we need to include a negative sign because it is compression. So V by L, V is velocity of the die and L is the length at any instant. So during compression, the length of the specimen decreases. As the length of the specimen decreases, the true strain rate, it increases. As L decreases, the true strain rate increases. So to carry out the compression test at constant strain rates, it is very, very difficult, because as the length of the specimen, it decreases, the true strain rate increases. So to carry out these experiments at constant velocity, it is very difficult. For the case of engineering strain rates. This can be carried out easily at constant velocity. Why? Because this is proportional to that of the initial length. This is based on initial length, whereas here it is based on instantaneous length. So as the length decreases, the strain rate increases. So accordingly, the velocity of the die has to be modified in order to carry out the tests at constant strain rates. So the velocity also, it should decrease. The compression takes place, the length decreases, the velocity of the die also should decrease accordingly in order to maintain constant strain rate. So this can be achieved by means of equipment that is called cam plastometer to carry out the constant strain rate. For the case of compression, the true strain rate is inversely proportional to that of the instantaneous length. So cam plastometer is the device which is used to carry out the tests at constant strain rate, where this cam, it controls the velocity of the die. The velocity is also decreased in proportion to the length as the compression takes place, so as to maintain a constant true strain rate. So this is about the compression test, which has many differences with respect to the tension test. So these differences, there are many differences, like the true strain, it is higher in the case of compression when compared to that of tension, because necking limits the true strain to a very low values, whereas in the case of compression, very large true strains can be achieved. The application wise is also different. This compressive test, it is used mainly in certain applications where some of the components, they are subjected to compressive loads, as well as its main useful is in the case of metalworking processes. Mainly from this compression test, one can determine the flow stress of that material. This flow stress is important to determine the forming stress or forming pressure in the case of metalworking processes. So what is the stress required to form that component? So it depends upon the flow stress of that material and upon the tool geometry and lubricant conditions. So for that purpose, one goes for this compression test to determine the flow stress of that material. In the case of tension test, we have necking is a problem. In the case of compression, there is no necking, but there is friction that prevails at the interface between the surface of the component and that of the anvils. Then bulging, that is barreling, occurs. Barreling takes place. In order to minimize barreling, lubricants are necessary. For the cold deformation, Teflon sheet is used as a lubricant, and for very high temperatures, glass is used as a lubricant. And this is about the strain rates in the case of compression test. Move on to the torsion test.